introduction. Today I'm here to talk to you about my first year of research, which is on the effect of pre- and post-filtration thermal treatments on the microstructure and oxidation of whey protein phospholipid concentrate. So WPPC is the main co-product from whey protein isolate production. Sonali already has talked about some of its benefits, but basically because it's a rich source of milk fat globule membrane, there's a lot of lipids and proteins that can offer health benefits for people. However, despite the fact that there are all these possible benefits, it's considered low value, and when it gets used, it's mostly just used for animal feed. The purpose of my lab is to change the opinion on this and help people realize that WPPC can be a high value product. WPPC is produced in large amounts in the US because it is tied to whey protein isolate production. The way that you get directly from cheese making has a lot of fat, has a lot of sugars, and so it goes through various separations to take out the fat, take out the sugars, concentrate the proteins, and then ultimately end up with whey protein isolate and the retentate whey protein phospholipid concentrate. Along the way, it might undergo a variety of heat treatments, such as in the milk form before the cheese making, as whey if you want to maintain food safety throughout the processing, and then at the end, it might undergo further processing prior to consumption. Heat treatments can vary a lot, but the ones I'd like to highlight here are batch pasteurization, because that's a very sort of gentle pasteurization technique. HTST, which is very common for like the milk that you might just get from the grocery store, and spray drying, which is also a preservation method, removes all the water, and you can have those nice powdered ingredients. Now, these heat treatments can cause issue because they will help the proteins tend to aggregate under the heat, and that makes it harder to get higher yield whey protein isolate and can also denature some of the interesting proteins. So the purpose of my research is to understand the alterations that are going on with WPPC proteins during these thermal treatments and processing, and using this information to inform for higher efficiency processing strategies so we get better WPPC and WPI ingredients. To do this, we, for the past year, have been doing lots of in-house batch WPPC production. We made two types. One type we're going to refer to as batch WPPC, and in this case, with the help of CDR, we took a lot of raw milk, made whole milk cheddar with the raw milk, and then skimmed off the fat. This raw skim whey was about 250 gallons at this point. We put it through a gentle batch pasteurization because if we didn't do that, the enzymes and microbial activity was just so high that the pH would just drop throughout the day as we processed. After that pasteurization step, we ultrafiltered with 10 kilodalton membranes. This resulted in about 50 gallons of whey protein concentrate, so about 5x concentration, and then we microfiltered with 0.1 micron pore size membranes, so a larger pore size to get our whey protein isolate and our whey protein phospholipid concentrate. We had roughly 5 gallons of WPPC by the end of this, so a 10x concentration, which just goes to show why we have to do this in such a large scale, because much smaller than that, and you wouldn't have enough to conduct all of your experiments. Additionally, we did spray dry a portion of it because that is common in industry. The other type of WPPC we made is I'm going to refer to as 2x HTST WPPC, and this was a lot closer to what you would get in industry. In this case, we got whole whey from the Babcock dairy stores. They made cheddar. We took that whey, skimmed off the fat, put it through an HTST pasteurization, and resulted in skim whey that had been pasteurized twice, once as skim whey and once as milk prior to cheese production. Ultrafiltered and microfiltered in the same manner, and resulted with a WPPC that was more akin to the WPPC that industry makes. Additionally, some further heat treatments were applied post-filtration, such as spray drying, retorting, which is a very extreme heat process and makes everything kind of come out like a cooked egg, and an additional HTST treatment. To make sure that our WPPC was around the same specifications as industry, we consulted the American Dairy Products Institute website to see the sort of standards they had for fat and protein on a total solids basis, and we very easily surpassed that, so that was good. And then finally, equipped with our whole list of WPPCs with different treatments and different processing, we started running analyses. Now, I realize that there is an awful lot of samples there, but the biggest things I want you to just remember is that batch WPPC is about the absolute minimum amount of heat we could apply to the system. And anything other than that has undergone HTST treatments and or spray drying or retort and so forth. I'm going to start by talking about the microstructure, and with this, I'm going to begin with the microscopy images. These were taken at 100x. The proteins are dyed green, the fats are dyed red. And what we can see here is that batch WPPC, which experienced the least amount of heat, has much smaller milk fat globules than that of the WPPCs that were made with HTST treatments. This is good news because that agrees with the mean diameter size of this particle size information we received using laser diffraction. Laser diffraction measures particle sizes in a solution on a micrometer scale, so larger particles. Additionally, we added ETTA to break up any casein micelles, so hopefully none of those were part of the reading. And we can see batch WPPC significantly smaller than the HTST WPPC's milk fat globule size. Additionally, if we look at the particle size distribution, these two WPPCs have not undergone any post-filtration heat treatments, and they have a pretty uniform distribution. There's like a small hump around like maybe 75 micrometers, but other than that, there's a nice solid peak. As soon as we started applying heat to WPPC through spray drying or HTST treatments after filtration, the particle size kind of starts to go nuts. It gets a lot larger. You get this very multimodal distribution. This correlates with the data we were able to collect using dynamic light scattering. This is a technique that lets you measure particle sizes on a nanometer scale, so much smaller than the milk fat globules. And while that gets measured, it also measures the polydispersity index. Polydispersity index is a measurement, or it's a unitless measurement, on how uniform the particles in a solution are. A higher polydispersity index means that your particles are less uniform in the mixture. And what we found was that the particle size, as it increased, correlated with an increase in polydispersity index. This agrees with that multimodal distribution that we started to get with the increasing particle sizes. Additionally, on the nanometer scale, the spray drying did not significantly affect the particle sizes of the liquid WPPCs they originated from. However, post-filtration treatments like additional HTST pasteurization and the retorting did result in much higher particle sizes. Finally, we did do zeta potential, which is a measure of the total net charge of all the particles in the solution. It can kind of help us get an idea of colloidal stability. However, they were pretty uniform across the board with a few differences, but even then, they're basically the same. Everything had overlapped with at least 2 other samples. Following microstructure, I'm going to talk a little bit about protein. So to get an idea of the protein profile, I ran a reducing gel with SDS-PAGE. So that had DTT added to it to break up any disulfide bonds. And for the non-reducing gel, there was no DTT added. Right away, we can see that the protein profiles are very similar. There's milk fat globule membrane proteins that are larger, like xanthan oxidase around 150 or butyrylation around 55. Additionally, underneath that, we have caseins. Now, you probably expect casein to end up in the cheese, which is true, but it's not a perfect conversion, and so any caseins that were left over in the whey are going to end up basically in the WPPC. Underneath that, we have our nice little whey proteins. Additionally, we had some large aggregates stuck in the loading wells of the non-reducing gel. These disappeared, for the most part, in the reducing gel, which is indicative of disulfide bonding. They don't really disappear for the retorts, but the retorts don't solubilize all that well because you're essentially trying to solubilize a cooked egg. This is Fourier transform infrared spectroscopy. So this is a method that allows you to sort of approximate the secondary structure of proteins using spectroscopy. These samples were all standardized to protein, so any differences in the peak height or the peak shape is due to changes in the secondary structure. If you have more alpha helixes or beta sheets versus an unordered structure, that peak shape is going to change. Now, I need to continue some deconvolution on this, so I don't have the exact numbers, but right now we can qualitatively look at this and be like, yes, it appears that the batch WPPC, which experienced the least amount of heat there in the purple, has a different peak height and peak shape than, say, the very, very heated WPPC that went through retorting. Continuing protein sort of denaturation, this is beta-lactoglobulin quantification using HPLC. So beta-lactoglobulin has thiol groups that like to bind up with themselves, bind to other proteins like caseins or milk fat globule membranes, and basically this is an issue because if you get very large protein aggregates like this, they're not going to go through the membrane very easily into the whey protein isolate. This method was done using a standard that did not have any complexes in it. So if we did have whey proteins, beta-lactoglobulin whey proteins, complexed with caseins or something like that, it would not be included in this quantification. And what we can see is that our batch WPPC, which had the least amount of heat treatments, also had significantly highest number of native structured beta-lactoglobulin compared to that of ones with heat treatment. Thus, again, indicating, okay, this heat, it is affecting the proteins, their structures, and their aggregates. Finally, we did a bit of lipid oxidation. These are both spectrophotometric methods. One measurement was the peroxide value, which measures the primary oxidation product of lipid peroxides. And when I did this, I found that there was no statistical differences between the primary oxidation products of content of each WPPC, no matter what heat treatments had been applied. However, we also measured the secondary oxidation products, which in this case we used malonylaldehyde and used the T-bars method. So in this case, we found that batch WPPC, which had experienced the least amount of heat, had actually the highest amount of secondary products, more than any other. And then the WPPC that had the least amount of T-bars was the WPPC that had gone through 2 HTST treatments. And so my current hypothesis with this is that the HTST treatments are behaving in a similar way to the preheating step that industry sometimes does with spray drying before spray drying dairy products, which can expose viral groups and will act as antioxidants. The final takeaways is that yes, we are able to observe protein structural changes in the proteins on the secondary and microstructural level, and these are linked to heat treatments. Additionally, these heat treatments are not all necessarily bad. HTST treatments appear to protect against secondary oxidation for the WPPC lipids. So for future steps, we're going to look further into that secondary oxidation products and why they're getting protected, why WPPC is being protected by HTST treatment, as well as looking a little bit more into the proteins, structures, binding, and so forth. And I would just like to give a quick acknowledgement to the National Dairy Council and Dairy Innovation Hub for helping fund my research, as well as a large number of people and professors over at the Department of Food Science, because this is a very large project and I could not have accomplished this without all their help. Center of Dairy Research for their resources on how to use membrane filtration and the help with making the raw cheese, and Babcock Dairy Store for providing the HTST whey. And I'll take questions.